Hey, welcome back for Recursive Definitions Part 2. The directions to start off today are to find a recursive definition for each of the following sequences. In Part A, the sequence is 81, 27, 9, and 3. So this is T1, this is T2, this is T3, and this is T4. What are you doing each time? Well, you're clearly multiplying by some fraction. And in this case, it's 1/3. You're multiplying by 1/3 each time. This is a geometric sequence. But I asked you to write a recursive definition. And remember, a recursive definition has two components. And if you don't have both components, then you don't have a recursive definition. You need the initial condition, which is the first term. You have to know where the sequence began. In this case, it's 81. Again, that's called the initial condition. And then you need a recursion equation. Well, to find any term, any nth term, you simply take 1/3 times the previous term. Let's check it. So, for example, what would t sub 4 be? We already know it to be 3. But let's make sure the formula works. Take 1/3 times t sub 4 minus 1. In this case, 1/3 times t sub 3. In this case, 1/3 times 9, which is 3. So it looks like our recursion equation is working just fine. But remember, you need both components. What about this for sequence? 1 goes to 3, and 3 goes to 7, and 13 goes to 21, and 21 goes to 31. So this is T1, term 1, term 2, term 3, term 4. I recommend doing this, especially when it's not obvious what the pattern is, and term 6. Here, N is position 1, position 2, position 3, position 4, position 5, and position 6. Well, the initial condition is always pretty easy to do. What's the first term? It's 1. But now, how do you get from one term to the next? How do you get from one term to the next? And this is where it gets saucy. So what I start doing is I look for patterns, guys. Help me find a pattern. To get from 1 to 3, you add 2. To get from 3 to 7, it looks like we add 4. 7 to 13, you're adding 6. 13 to 21, you're adding 8. 21 to 31, you're adding 10. Do you see a pattern? Well, you're adding 2 more each time, but do you see a pattern related to your ends? Related to your ends. I do. It looks like we're doubling the end values. Oh, wait a minute. No, we're not. We're doubling the previous n value. It looks like here's the formula that works. Remember, it has to include the first term. You're taking the previous term plus twice the previous n. The previous term plus twice the previous n. Let's check it to see if it works. Are you ready? Here we go. T sub 4. The previous term, 4 minus 1, plus twice the previous n, 4 minus 1. That'd be t sub 3 plus 2 times 3. Well, t sub 3 was 7 plus 6, 13. Is t sub 4 13? Ding, 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 ding. It worked. Oh, yeah. All right, that's right. What about t sub 5? Would be the previous term plus twice the previous n. That should have been a 5, not n. Well, that'd be t sub 4 plus 2 times 4. T sub 4, 13. Plus 8, 21. Oh, yeah. Oh, yeah. T sub 5, it's 21. Nice. So I would guess that our formula, our recursion formula, is going to work. Now, just for giggles, if you'd like an explicit definition, you could pause the video and see if you can figure one out. And I'm going to go ahead and give you the one that I found. Here it is. The nth term is always equal to the term you're interested in squared minus the previous n. Another way to write that would be n squared minus n plus 1. That also will help you. But that's an explicit definition, whereas we wanted a recursion, or recursive definition. Okay, now here's an application problem involving a recursive equation. Read along with me. The population currently is 5 million. The population currently is 5 million. Annual population growth is 1% of those in the country and 20,000 immigrants each year. So it grows by 1% of those who are already in the country, plus it adds $20,000. Write a recursive definition to describe the population. So we're going to take the previous population times the 1% growth plus the 20,000 immigrants. That'll get you your new population each time. So check it out. Our recursion equation, initial condition. In this case, we're not going to call it P1, we're going to call it P0 for like year 0 was 5 million. That's what we're starting with, 5 million people. And your formula for the population after n years is always equal to the previous year times 1.01, right? Because it's growing. 1 plus 0, 1. That's 1 plus r, 1 plus 0.01. Hopefully you remember that. Plus the 20,000 immigrants who are coming into the country, who are not already here. So find P sub 1. Well, that would be P sub 0 times 1.01 plus the 20,000 immigrants. Well, we started with 5 million people times 1.01 plus the 20,000 immigrants. Answer, 5,070,000. That's the population after 1 full year has elapsed. What about the population after 2 years? Well, it's the previous year times 1.01 plus 20,000 equals the previous year, which is not 5 million. It's 5,070,000 times 1.01 plus 20,000, and that actually equals 140,700. And then finally, the population after 3 years would be P2 times 1.01 plus 20,000. That equals 5,140,700 times 1.01 plus the 20,000 immigrants who are going to come in that year. Answer, 5,212,107. So there was just an example of using a recursive definition to estimate the population of a particular country after 1, 2, or 3 years. That'd come in handy if you're a government official wanting to decide where taxes should be allocated, how to conduct a census, and how many people should be found within the census. So, good applications for the stuff that you're learning. That is all for Section 2. Hope you enjoyed it. I'll catch you later. I'm out.